So let me just start off with a discrete group. And then as we all know, there's the left regular representation. This looks like this. And from this, then we build some operator algebras. So the main one I want to talk about is the group C-star algebra, or the reduced, should I say. And because our group is discrete, it consists of, so has a dense subset. Like this, where the coefficients are just scalars, and only finitely many of them are non-zero. And then there's also the group unknown algebra. Which is the second commutant, or if you prefer, the second commutant of this set. And lastly, the Fourier algebra. A of G. And A of G is the collection of coefficients of the left regular representation. So it's the algebra of functions from the group to the complex numbers, such that U of S is the matrix coefficient. For some 0 to be there. So all these spaces will appear at various times, but I mainly want to talk about the group C-star algebra. But the Fourier algebra and the group unknown algebra will form one. So they're all related in the following way. And the group unknown algebra is the dual of A of G. So having defined all these spaces, then we're interested, or at least I'm interested, in knowing what properties of the group these algebras capture. So our properties of G reflected by or 1 over G or A of G. So again, I'll focus on this question. just pick your favorite property of G. So say G amenable implies C star reduced with G is what? Or your favorite C star algebra property maybe. So C star lambda with G nuclear implies what? G. You can do this with whatever property you like, maybe that stands for probably T we saw earlier. Or you can ask this question about Vn of G or A of G. So yeah, I think this is a natural question. And an important result in this direction is given by Lance. I think 73. And Lance proved that if G is a discrete group, then, well, he answered this very neatly, basically, you might guess. Then G is amenable if and only if the reduced group C star algebra is nuclear. So just as an aside, by the way, in this talk, nuclearity I will take to be the completely positive approximation property. So there is a net of completely positive maps on the C star algebra, which converts the identity in the point known topology. So, yeah, maybe you're more familiar with nuclearity in terms of the min and the max tensor products, but this is the definition I'm going to be thinking about. So, I just want to highlight one bit of the proof that Lance gave that's relevant to this talk because it uses Herz Schur multipliers. So amenability is factorized by the existence of a sequence of positive definite Herz Schur multipliers on G, which are finitely supported and converge the identity in point known. Converge to, let me write it like this, the constant function 1 pointwise. So yeah, I guess you wrote this characterization yesterday, or you didn't say Hertz Schur multiplier, but yeah. So this, although Lance doesn't use this language again, this is really what's going on in his proof, that G amenable implies C star reduced of G in nuclear. So now, let me say exactly what I mean by a Hertz Schur multiplier. So, a function from the group to the complex numbers is called a Hertz Schur multiplier. If it's a completely bounded multiplier of the Fourier algebra. So let's say M sub U on the Fourier algebra where M sub U of V is just the pointwise product U times V. So it is a completely bounded map. So here, what I mean to indicate by this is that the pointwise product, if you use just any function, the pointwise product doesn't necessarily land in A of G. So that's one of the properties of U that we're asking for. So we're asking for the pointwise product to again be in A of G, and that this map is completely bounded. So yeah, I should say that this this characterization was given by Brzezinski and Fender in the 80s, I think. And because of this geology here, we can characterize it in terms of the group von Neumann algebra or the reduced group system algebra. So since we have this geology, then the adjoint MU star is a map on the group von Neumann algebra. It's completely bounded. And it's very straightforward to calculate how it acts. So these lambda sub S generate the group von Neumann algebra. So we want to look at how it acts in the generators. And pairing with an element of AFG, we just get and then by definition of the geology here, this is U of S. p of s, which is just this. So in other words, u of s. Yes. So now then, mu star restricts to a completely bounded map which I'll write S sub u on the reduced C-star algebra and it acts in the same way. So I'll write it like this: SU of some AF. It's just some U of F. So now this is the thing about Herz Schur multipliers that I want to focus on. And returning to Lance's proof. So what Lance did was then say, so there's a net UI of positive definite Herz Schur. Each UI is dynamically supported, and each UI, or well, the sequence UI converges to the constant function. It was. And then how this proof goes then is that if the UI are positive definite, then the S of UI that I just introduced are completely positive. The UI have infinite support means that the S of UI are finite rank. And the UI converging to one pointwise means that the S of UI converges to the identity map. In point one. And this is exactly nuclearity. So these three conditions give.
In principle, would it be possible to state the definition on C star lambda of the Hertz Schur multipliers, or does that not quite work?
Yeah, they are in fact equivalent. Yeah, so I could have just written C star lambda G completely bounded maps that act in that way. But since I had a little time, I wanted to show the original definition. Yeah, so when I define some more generalized versions, I'm just going to stick to the C star algebra level. So what I've been trying to get at here is that I said at the start that we wanted to link properties of the group to properties of the of the reduced C-star algebra, and it seems like this connection through the Hertz Schur multipliers is a good way of doing that. And building on that then, along came Howard and some others, and they said, well, what about if we try to run the same proof as Lance did, but sort of play with the conditions involved a bit and kind of see what that gives us on the C-star algebra level, or what that gives us on the group side. So sort of the idea is to run a similar argument to the one I've just indicated, but change some of the conditions and see what properties of C-star algebras you get, or what properties of groups you get. So an example of this program is weak amenability. Where we basically take these conditions but forget about the positiveness. So if there's a, let's say, uniformly bounded, okay, maybe that'll be enough. There's a net of Hertz Schur multipliers which are finitely supported. They converge to the constant function pointwise. And the Hertz Schur norm is uniformly bounded. And then if you run the same program, so you have being Hertz Schur implies that the associated maps are just completely bounded this time, no positivity around. So finite support again implies finite rank. And converge to the constant function again implies converge the identity. And then what this gives you is a property of the group C-star algebra called the completely bounded approximation property, or CBAP. which is again like nuclearity but with no positivity around. So, another example is the higher property. Where this time you keep positive definiteness, but you ask that the functions be vanishing in infinity. So was definite. Vanish in infinity, and they converge to one. Pointwise. And as a property of the group, this is already interesting because it's the opposite to Castan's property T that we saw earlier. In the sense that if a group has both this property and Castan's property T, then it's finite. And what you get is the rather unimaginably named higher property of G star lambda of G. I won't tell you exactly what it means, but it involves approximation in L2 of let me solve this one. So continuing in this way, there's a few other properties that I don't have time to mention. What we get is sort of a hierarchy of properties of groups, starting with amenability being the sort of the best, most well-known one anyway, and getting weaker. And on the other side, a property of a hierarchy of properties of the C-star algebras, and equivalent conditions linking through Hertz Schur multipliers. And one last consequence of this is that, well, three groups, say the free group and two generators, we all know is a non-amenable group. But in fact, they're weakly amenable. So, in a sense, although they're known as being bad for non-amenable, they're not so bad. They have the sort of next best thing. And what this means is that, as I just said, the reduced C-star algebra of the free group has a completely bounded approximation property, but it's not nuclear because nuclearity is equivalent to amenability. And this was discovered by Hagra and actually answered an open question, namely, is nuclearity for C-star algebras the same as the metric approximation property for C-star algebras? And this example shows that that's not the case. And I think that's quite a nice idea. You have this property for C-star algebras that you can't tell apart. So you look at group C star algebras and then separate the property on the group side, go back over to the C star algebra side, and you get your answer. So now I want to move on from groups and talk about group actions and cross products. So let me just give you a very brief skim over cross products just for notation things. So a group G acts on C star algebra A by a group homomorphism alpha from the group into the polymorphism group of A. G is discrete, so we don't need to worry about any continuity issues. So together this data is called a C star dynamical system. And from this system then we can build another C star algebra called the cross product in a very similar way to the group C star algebra was built. So called the reduced cross product. Right, like this. Which somehow captures, it's a C star algebra which, as you said earlier, captures the action somehow. And like before, it contains a dense subspace. Consisting of finite sums which I'll write some AS lambda S. Again, but this time the coefficients come from the C star algebra. You maybe know that I'm cheating a bit here, like we'll have to inflate the left regular representation and twist the action of A, but this is the notation, that's very convenient. And the action is captured at this level by the relation lambda S A lambda S star equals alpha S. Okay, so that's why the action appears in these things. Yeah, I should say that when C star algebra is just complex numbers, then what we've constructed is the reduced group C star algebra that we had before. So now, what I told you up till now has all been known. Now we come on to joint work with my supervisor, Ivan and Ludmilla Frosty in Gothenburg. We've developed Herz Schur multipliers of C-star dynamical systems. So here is where I'm going to take advantage of the fact that we can define Herz Schur multipliers in the C-star algebra level, because it's much more difficult to find some analog of the Fourier algebra that I had before. So let me remind you quickly. So let's see. Function of the group is Herz Schur. If and only if the map on the C-star algebra like this. It is completely bounded. So what we did was replace the function from the group to the complex numbers with the function which we write as f for some reason from the group to the completely bounded maps on A. So we call it a Herz Schur multiplier of if, and then we write down a version of this condition. So remember the A's now come from the C-star algebra. If this match is completely bounded. So this is what our definition looks like when the group is discrete. We have the definition as well for locally compact groups, where it's a bit more complicated to write down. But this is the discrete version. So I just want to highlight here, US is a scalar and AS is another scalar. This time AS is an element of the C-star algebra and F of S is a completely bounded map on the C-star algebra. So in principle you could maybe define this, and some authors have done, like Dong and Ram, where F of S is just another element of the C-star algebra and we multiply. But we've gone for something a bit more general here. And it turns out that this notion works quite nicely. So is there anything else I want to say? So yeah, if again, if A is just the complex numbers, then we recover the classical Herz Schur multipliers that I've been talking about so far. And the other thing that I didn't tell you is that parallel to the theory of Herz Schur multipliers is a theory of Schur multipliers, which generalizes Schur multiplication of matrices. And Schur multipliers and Herz Schur multipliers are linked. And the main part of my thesis is developing this link at this level as well. So we came up with a more general version of Schur multiplier. showed that they're linked to these things here. But anyway, what I wanted to get to is that now we have the tools to play the game that I played before with groups at the level of reduced cross products. So we can talk about approximation properties for reduced cross products in a new way. Or let's say reduced cross products. So of course people have already studied these to some extent, and there's a lot of results that look something like if G is amenable, then A is nuclear, if and only if the cross product is nuclear. Or maybe you could say, you know what amenable action is, if G acts amenably, then the same thing holds. But there's also some examples that show that the assumption of an amenable group is not always necessary, especially if you replace, say, nuclearity by CBAP here. Then if you have an amenable group, then it works. But there's certainly examples that show that amenable groups aren't necessary for such a result to hold. The question is, what is necessary? So we can use our new Herz Schur multipliers to give a different characterization. And what we do is basically we write down exactly what we had before. So what we want say write it for the CBAP maybe, but what we want is we want these maps SF to be completely bounded. They need to be finite rank. They need to be converged to identity, and they need to be uniformly bounded. And then, well, the task is to come up with conditions on F. So what do each of these things mean for F? Well, F is Herz Schur multiplier of AG alpha. Implied by definition, we have this. So then there's some other things that I'm not going to write down that tell you what finite rank means and converts the identity means. And if we wanted to do nuclearity here, what we've been working on is what condition on F makes F completely positive. Then the same conditions here as well. And also we're interested in the Haggard property of a cross product, which has the same sort of flavour, if you like. And also what we want to do is try and phrase the existing results in this language. So if you know about amenable actions, you might know that it has a rather mysterious definition, and we tried to phrase a mutable action definition in this language and then run the program again and see what that gives us. Well, reprove the results, if you like. And so what I'm doing now is trying to collect up some interesting examples of cross products which maybe don't behave very well. For example, there's a well-known example. An example is that this group is weakly amenable. And of course this group is amenable. But if you form their semi-direct product, it is not weakly amenable. And the semi-direct product can be phrased as a cross product. So in other words, so I should say, sorry, this cross product is the same as the reduced C-star algebra of this semi-direct product. And if you go through the characterizations that I've shown you before, what we have is a weakly amenable group acting on a nuclear C-star algebra. That does not give the CBAP. That's rather confusing. So I'm interested in if anyone can think of any nice examples of semi-direct products or cross products. Let me know. I'm interested in kind of collecting these things and seeing what sort of counterexamples and examples we have and how they fit in with the program that I've indicated. So yeah, I think I'll stop there.
Questions or comments for the speaker?
I mean, with this last example, I guess one of the problems that the means on Z squared don't behave very nicely under that sort of thing.
Yeah, there's a few different proofs of that. One is that yeah, I think maybe that's what Hagar did originally. I can't remember how it goes. Yeah, but another way of showing it is that weakly amenable groups, if they have amenable subgroups, they have to behave in a certain way, and these don't.
Anyone else?
So I guess as far as I remember correctly, the important aspect of the amenable action is actually it is determined on the action on its center. I mean, so you don't need to consider the A itself, right?
Yeah.
So do you have? I mean, at least can you hope this kind of property for this weak amenability?
You mean, can you hope that
Yeah,
an
so
amenable action?
yeah, weakly amenable action can be characterized in terms of the action on its center, not on the A itself.
I have a feeling that, I don't know, I mean, I think this example shows that a weakly immutable action is really not a good notion, because you would want a weakly immutable action on a C-star algebra with a CBAP to give you a cross product with a CBAP, but this says that weakly immutable groups do not act weakly immutably. So yeah, I'm not sure if weakly immutable action is a fruitful thing to pursue.
Thank the speaker again.